When we first looked at our RC car design, we wanted the chassis. When we first looked at our RC car design, we wanted the chassis to curve in the front. We also wanted to feature larger cutouts in the backside to have larger rear wheels. We also wanted the entire chassis to be made of wood with a mixture of screws and adhesive to keep all the parts together. We also wanted metal machine parts for the axle, bearing mounts, and ball bearings and the overall steering design.
Here's our chassis design sketch. We decided we wanted cutouts for the wheels to protect it from being hit by other cars. We also wanted a rounded nose in case we hit other cars or a wall so that it would deflect the car rather than getting stuck. We decided that wood would be the best material to make this out of since it's relatively light and durable, and it would be easy to make this design with a laser cutter.
So here is our chassis CAD design. As you can see, it's very similar to the sketch presented before. A few important things to note are that we made the cutout for the front wheels larger so that the front wheels could rotate. We also increased the width of the chassis in the middle to account for components like batteries and housings. We also made the wheels in the back larger than the front so the car could be pointed downwards when accelerating for better aerodynamics and better stability. You can also see axles in the back as well as axle mounts, which are made from metal and plastic respectively. Inside the mount, there's bearings that help to rotate the wheels. And finally, in the back, we decided to have some extra wood to act as a bumper to prevent any damages from rear car crashes.
So for our first FEA of the chassis design, we did not have wheels because they did not fit properly on the axles, and so we just put the fixed geometries on each end of the axle and then put a force on the back of the chassis. And so as you can see, the axles have deformed the most, and so as you recommended, we did make them thicker for the final CAD design. But as a whole, the car looks to be intact and working well, even with the force applied.
Here's our drivetrain design sketch. We wanted to keep it as simple as possible to reduce losses due to friction in belts, etc., and to keep costs down since we had a budget. We decided to go with 2 timing gears and a timing belt. Since we decided at the beginning we were more focused on acceleration than top speed, we went with a smaller gear attached to the motor and a larger gear attached to the rear axle in order to trade speed for torque.
So here we have the CAD design of the drivetrain. The left is a side view and the right is a top view. We found the gears both available on McMaster that fit our specifications. So they're both made out of metal. The back one has 20 teeth and the front has 10 teeth, making it a drivetrain ratio of 1 to 2. Both gears are timing gears, and there's also a timing belt. So once the motor starts moving, the back gear starts moving, which transfers energy to the axle, which moves the wheels back and forth.
So calculating the top speed of the drivetrain, we focused on 3 forces: the drag force, the friction force, and the bearings and the friction force of the wheels against the ground. Adding those forces, we got our total force, and from that, we could calculate the motor speed and therefore the final linear velocity of the entire car.
I won't go into too much depth about the max acceleration calculation, but the main points were that we used a 2-to-1 gear ratio such that the torque experienced by the tires was double that of the stall torque of the motor. We analyzed 2 different sources of losses. One was the rolling resistance, which was simply friction lost to the ground via the tires, and then we looked at bearing friction because the bearings were actually going to produce a counter torque to what the axle torque was that we were trying to deliver to the tires, and so there was another loss there. Subtracting those losses out and using Newton's second law, we got to a max acceleration of 5.84 meters per second squared. To understand the functionality of our To understand the functionality of our steering mechanism, let's refer to the leftmost picture. The cross in the middle is the servo, and the 12 o'clock position is the arm that actually moves from side to side. So attached to that arm are two separate rods that jut out to an L-shaped piece, which connects to the wheel hub. If you look at those L-shaped pieces, there's a black dot. That black dot is actually a pivot. So when the servo rotates to the left or right, those two rods are actually going to push or pull those L-shaped pieces and in turn turn the tires.
So as you can see, we have the CAD model for the front steering mechanism. On the left, we have a side view, and on the right, we have a top view. We made a few changes from these sketches to the CAD model just to make it easier to model in SOLIDWORKS. The first being that the pivoting arm has one flap instead of looking more like a star. In addition, the connecting arms, we made them flat bars with holes that are concentric with both the pivoting arm and the connectors. And as you can see, we have a housing system that connects the servo in an upside down position, just so that we could have more space for the steering mechanism. And it's positioned in such a way that once the flap moves in a 45-degree angle, the connecting arms move, and consequently the entire steering system rotates.
The first part of the turn radius calculations is to calculate the max angle of the wheel turn. To do that, we went to the CAD, turned the servo 45 degrees, and then measured how much the wheel turned, and that turned out to be 35.3 degrees was the maximum angle of the wheel turn. Then to calculate the turn radius, we drew a perpendicular line from the turned front wheel, which was a diagonal line down, and then a perpendicular line to the straight back wheel, which is a horizontal line out. And the intersection of those two lines was the center of rotation. So then we created a triangle between the center of rotation, the front wheel, and the back wheel. And we knew the angles of the triangle, and we know that the distance between the front wheel and the back wheel is 8.5 inches. So then we were able to calculate the distance from the center of rotation to the back wheel using some basic right-hand triangle trig, and we calculated that to be 12.005 inches. Then we measured the distance from the center of the back wheel to the middle of the car, and that turned out to be 3.315 inches. The sum of those was the turn radius, which is 15.320 inches. In this slide, we have two short videos showing our working steering design and our working drivetrain design on SOLIDWORKS. On the left side, we have our steering design, which you can see as the servo arm rotates, the wheels also turn with it. And on the right side, you can see that as the DC motor rotates, the timing belt and the gear system work to make the back wheels rotate as well.
Manufacturing and assembling an RC car involves laser cutting the wood chassis, providing housing for the motor and the battery parts, plus 3D printing the steering rods, machining the axles and the axle mounts, buying bearings, the gears, the timing belt, and the wheels, and using epoxy to hold everything.